Hello everyone. I'm going to present my work collaborated with my fellow researchers, Saivardhan, Akshay, and our professor, Dr. G. Madhu. And my name is Alem Bharatwaj. So I'm going to present our work, Improvising the Learning of Neural Networks on Hyperspherical Manifold. Yeah. So the motivation behind this work is we have seen a lot of work going on face recognition and face identification, where they provided an angular margin objective functions, where they specifically mentioned they have used these objective functions on hyperspherical manifold, but we didn't find the actual theoretical justification, and the practical implementation was viable, and the performance was good, but we didn't find the actual shifting of sphere. So we actually used a method, stereographic prediction, which shifts the data from Euclidean manifold to a hyperspherical manifold. So, and we theoretically justify that this projection and by shifting into an hyperspherical manifold can be used as the decision regions. And we have experimented this work on standard classification image datasets, which are CFA10 and 100. And also we have implied on malaria dataset, which was acquired from National Institute of Health. And for the complete paper, you can find the link below. Yeah, so let's move forward. Okay, let's discuss what stereographic projection is. So stereographic projection is a map from an n-dimensional Euclidean space, which consists of origin to that of n plus 1th dimensional space, which is Sn, that is hypersphere of n dimensions, which does not consist an n plus 1th orthonormal basis. So we try to map this n-dimensional Euclidean space to hypersphere so that the point that linearly extends till en plus 1, but it cannot touch en plus 1. So during this meantime, while extending it till en plus 1, it touches on hypersphere at a point, and there is a point where the projection is actually implied. So diagrammatically, so this is a point on the real line Z1, and we try to project, we try to extend it onto a hypersphere of S1 and n plus 1. So E n1 E2. E2 is the orthonormal basis of S1. And we try to extend this till here, and the projection is implied at this point. It cannot touch E2, but it meets hypersphere at this point, and this is where the data lies. So we try to project the data such as Z1, Z2, Z3. So these are the projections: phi x1, phi of x2, phi of x3. In the similar fashion, you're going to a two-dimensional space. So Z is a two-dimensional point, and you try to project on S2, which is, so while you're trying to project from Euclidean space to Euclidean space of some dimension to an hypersphere of some other dimension, there'll be an extra dimension, and you have to be careful for that. So while projecting from Z1, you will have an additional dimension. So this is the point Z1, but whereas phi of x1 has 2 coordinates. So here Z has 2 coordinates, but phi of x will have 3 coordinates. Yeah. So we try to justify with the theorem. So a unit hyperspherical manifold is always convex and connected. So therefore, what we do is we convert this. So if the Sn is convex and connected, does it aids the decision process? Yes, it does. So as unit hypersphere possesses these two properties, we can definitely use it as decision region. So the theorems and the proof for the propositions are provided in our work. You can actually go and check it there. Yeah, and yeah, the angular margin objective function that I have mentioned earlier have tried to project on hypersphere, but they didn't. And with the help of stereographic projection, we actually project these set of data samples onto hypersphere. So let's have a basic look at on this regular functions, objective functions. So this is a basic softmax. So it discriminates between two data points for different classes. And if the decision boundary is given by a red dotted line like this, and the two classes are being discriminated like that. And then I get into a hyper sphere phase, where this work actually improves the intra-class similarity and inter-class discrimination. So parameter W, where this actually helps to improve the intra-class similarity. It shrinks the intra-class similarities. It gets the data very closer, and it actually the boundary actually pushes it to move the angular boundary theta actually tries to push it away from the different classes, like the class 1 and class 2. So the two, and here the theta acts as the angle between class 1 and class 2, and it tries to move away. And whereas the interclass similarity, the class 1 gets compact and the class 2 gets compact. So this is how the sphere phase is implemented. And in the same phase, the sphere phase is angular manifold, whereas the cos phase is manipulated on cosine space. So here the S is the cosine angle between the two classes. So yeah, and this is an perceptual visualization. So it's just an intuitive way, and it looks like that. And the cos phase actually outperforms sphere phase in face recognitions. Tasks such as outperforming in LFW, megaphase, and all those challenges. And getting to the arc phase, where they actually integrated both the cos phase and the sphere phase, and with that they actually had a huge variations by using the hyperparameter M, and this hyperparameter M is called a margin. So they maximize the margin, they minimize, they had the tuning, they have certain standard hyperparameter tuning to that. And you can look into the paper, and you can just have look into it. And when coming to the broad phase, this is actually implemented as using arc phase as objective function. And instead of the basic mini batch learning, they have introduced an NQ method, which actually contains that embedding vectors of previous iterations. Yeah. So yes, so we conducted experimentations on CIFAR10 and CIFAR100 datasets. And yeah, the CIFAR100 dataset actually consists of the samples of 50,000 training samples and the 10,000 testing samples. And CIFAR10 goes the same, but whereas individual classes are differ, here there are like 10 classes, and here there are 100 classes. And before for training, we used ResNet as an encoder. So we used a basic standard CNN ResNet. We gave the input, and we just acquired feature vector, and we classified with a two-layered feed-forward neural network by implying the stereographic projection, and without implying the stereographic projection on different the objective functions as explained previously. So yes, and we haven't used any augmentation. We just performed our experimentations on pure data sets, and we have experimented by performing, like, calculating the accuracy scores for like 5 times, and we have computed the mean and standard deviation. And during experimentation, we have observed that the broad phase, which the present state of the art 2020, so the state of the art obtained a higher accuracy score when they have the projected data. That is when we apply the stereographic projection, we got a highest accuracy score for the both C410 and the 100, and you can see the results. And also we have experimented on NIH, National Institute of Health malaria dataset. But as the spear phase, cos phase, and the arc phase, the cos phase and arc phase are the mediocres. So we just eliminated them. So we just tried on categorical cross entropy, plain categorical cross entropy, spear phase, and also broad phase. So what we observed is we got, when we apply stereographic projection, we got a good scores. And when we apply CC, that there is a leverage of 1%, near close 1%, and for spear phase, and near close 1%, and for broad phase, it's near close 0.8%. So yeah, so you can get into the differences and all. So yeah, thank you.